measured in Newton per coulomb, force per unit charge. If a charge Q coulombs is placed in an electric field E Newton per coulomb, what will be the force on the charge? Tell me, what do you understand by an electric field E? E is the intensity of the field. This is the force per unit charge. Now, in this field, if you place a charge Q, what will be the force that charge will experience? It will be that field multiplied by Q. Why? Because by definition, field is the force per unit charge. Therefore, the force on a charge Q will be the force on unit charge multiplied by that charge. So by definition, E is the force on 1 coulomb of charge. Therefore, force on Q coulombs of charge placed in that field will be F, the force, equal to Q multiplied by E. That means whenever you place a charge in an electric field, that charge will experience a force. In the same way, whenever you place an object in a gravitational field, it experiences a force. This object is being pulled by the earth. It experiences a force, and that's why it falls. In the same way, a charge Q placed in an electric field E will experience a force given by F equal to Q times E. The charge Q will accelerate. Whenever there is a net force on an object, that net force will produce an acceleration. Now, what is the relation between force on an object and acceleration? F equal to ma, is that right? We will look at that as we go on, and we use this concept to solve problems. Now, here I have a positive charge placed at a point. That means all around it there is an electric field. So what happens if I place an electron here? That electron will experience a force. How much force? The force on it will be its charge multiplied by the electric field. Now watch what happens when I place an electron there. There's an electron there. It is falling towards, just like my basketball falls towards the earth. If I place an electron there, it will fall towards that positive charge, because all around here there is a field produced by that positive charge. If I place the electron here, I can place the electron anywhere I want. I would like you to watch the little arrow on the electron. Now you can see as the electron nears the positive charge, the arrow grows. Is that right? The arrow becomes bigger. What does that mean? That means the electric field becomes greater. Where is the electric field greater? Is it near the positive charge or away from it? As you come closer and closer to the charge, the electric field becomes greater. There you are. Okay, we will use that concept also as we move on. We know that electric field is a vector quantity. It has a magnitude and a direction. Now, what is the magnitude of the electric field at a point distance r from a charge Q? The magnitude is E equal to kq over r squared. Now let's talk about the direction of an electric field. What is the direction of an electric field? Well, to determine the magnitude, we used a test charge. What is the test charge we used? A unit positive charge. We will use the same in determining the direction of the electric field. The direction of an electric field is the direction in which a positive test charge would move. So if you place a positive test charge, the direction in which that positive test charge would move is the direction of the electric field? Well, since a positive charge will move away from a positive charge, the field due to a positive charge is directed away from it. Is that right? If you have a positive charge and if you place a positive test charge near it, what will happen to that positive test charge? It will be repelled away. That means the electric field due to a positive charge will be directed away from it. In the same way, the electric field due to a negative charge will be directed towards it. Now, if I have a negative charge here, and if I place a test charge, a positive test charge, it will move towards the negative charge. So, the direction of the electric field is defined in such a way that the electric field is directed away from a positive charge and towards a negative charge. Let's illustrate that. Now, here I have illustrated that. Tell me, here you have electric field all directed towards in here. What kind of a charge is this? Well, this is a negative charge. The field due to a negative charge is all directed towards it. In other words, if I place a positive test charge anywhere here, it will move towards that negative charge. Whereas, look at the field due to a positive charge. If I place a unit test charge, a test charge is always positive. If I place a positive test charge anywhere here, it will be repelled away. That means the electric field due to a positive charge diverges from the positive charge. Let's now talk about electric field lines. Once you understand how the direction of the electric field is defined, we can now understand electric field lines. The intensity and direction of an electric field can be better understood by drawing what are called lines of forces called field lines. What is a line of force? Again, you bring back our test charge. A test charge placed inside an electric field will experience a force, and due to that force it will move, and the path that it will follow is called a line of force. So what is a line of force? A line of force is the path taken by a positive test charge. Remember, our test charge is our guiding charge. So a line of force is the path taken by a positive test charge placed in the electric field. Since a positive charge always moves away from a positive charge and towards the negative charge, the field lines will always originate at a positive charge. Is that right? Lines will be starting at a positive, going away from it and going towards a negative charge. Did you understand that? A line of force is the path taken by a unit positive test charge. That means if you place a unit positive test charge near a positive charge, it will move away and it will move towards the negative. That means the path taken by that test charge will be directed away from a positive charge and towards the negative. Alright? And so a field line will start at a positive and end in a negative charge. Now, let's now talk about some properties of field lines. We can summarize the properties of field lines. Property number one, field lines always originate at a positive charge and terminate at a negative charge. Is that right? It's not difficult to understand. Suppose I have a positive charge placed here and a negative charge placed there. And I have a test charge. A test charge is a unit positive charge. You can see that will move away from the positive and towards the negative. If you place it there, it will go that way. If you place it there, it will go that way. In other words, these are what I called the lines of force, the field lines. So a unit test charge placed near this positive charge will move away from it and move towards a positive charge. Field lines always originate at a positive and terminate at a negative charge. Second property, the density of the field lines, that is the number of lines per unit area, is proportional to the strength of the electric field. In other words, what it tells you is, if the field strength, if the field is very strong, the field lines will be very crowded there. Whereas if the field is very weak, the field lines will be widely separated. Let me show that here. Now, if I have a positive charge here, look at the field lines I can draw. I can draw a large number of field lines, and I have drawn two circles on it. You see, these are all paths that will be followed by a test charge. Now look around here. The field lines are rather close to each other. As you go away, the field lines are separated. Now tell me, where is the strength of the field maximum? Is it here or here? As you move away, the field becomes weaker. So the density of the field lines, in other words, how close the field lines are, is proportional to the strength of the field. Where the field lines are closer, the strength of the field is greater. That is what the second property says. Well, I have a diagram here. You can see where I have this halo-like ring. The field lines are very close to each other there. As you move away, the field lines get more and more separated. That means the field becomes weaker. Alright? The field lines are farther apart here than here. Therefore, the strength of the field is much greater here than here. Property number 3. The number of lines originating from a charge or terminating at a charge is proportional to the magnitude of the charge. In other words, the lines will be crowded around a large charge and less crowded around a small charge. Well, I'll illustrate that in a minute. Property number 4, field lines always repel each other and they never cross. You see, a field line is actually the path taken by a positive test charge. If two positive test charges move, can they ever cross each other? No, because positive charge always repel a positive charge. And that is the meaning of this property. Field lines can never cross each other. They always repel one another. The strength of the field in a region is uniform if the field lines are parallel. Now, parallel field lines indicate that the strength of the field all over is the same. But that is understandable from property number 3. So go through these properties and make sure that you understand the meaning of these. Well, here I have illustrated